Hey guys, in this video we're going to learn how you can create a deep learning model that recognizes traffic signs from images. And this is really important, especially when you're building, for example, self-driving car, because you would want to first detect traffic signs, and then you would want to classify or recognize them. So one of the largest datasets that we have to date is the German traffic sign recognition dataset or benchmark, and it contains over, let me go in here, this is the website of the dataset, and it contains over 50,000 images in total, which are of course annotated, and it contains more than 40 different traffic signs. So we have single image multi-class classification problem, and here are some of the examples that we have in the traffic signs. So given this amazing dataset, let's go ahead, download it, and build a PyTorch model using a pre-trained ResNet model, learn how to fine-tune it or do some transfer learning with it. And after that, we're going to see how we can basically predict what traffic sign there is on the image. So the first thing that I'm going to do is to open Google Colab notebook. And in here, we are going to check first that the runtime is Python 3 and we have a GPU acceleration enabled. My notebook is already connected, so I'm going to check the video or the GPU card that I have. NVIDIA. And we have the P100, which is great. Next, I'm going to just copy and paste a lot of imports. And we're basically importing Torch or PyTorch, NumPy, Pandas, and doing some plot setup. Next, I'm going to download the dataset itself using wget, and the command will be available in the notebook that I'm going to link down into the description. While this is downloading, I'm going to go ahead and paste the command that I'm going to use to unzip this dataset. And it's the interesting thing around this is that I'm using double Q in here, which will basically not allow any verbosity from the unzip command. And if I check the data in here, we have the zip file, which is 263 megabytes, and we have the extracted dataset. We have the name of the dataset or the benchmark, we have final training, then images, and each subfolder in here is basically a single or a bunch of images that are related to a single traffic sign. So let me go ahead and basically get all of the traffic sign folders. And I'm going to use the autocomplete in here, final training, and then images. Alright, I have this now, and I'm going to check the number of traffic signs that we have. It's 43. Alright, and something interesting about this dataset in particular is that we have the images which are stored in this very, at least strange for me, format ppm, but OpenCV is able to handle this format very well. And I'm going to do some exploration on this dataset. Of course, we have a lot of images, and I'm going to paste in basically two helper functions. The first one is going to be show image, and we are basically using OpenCV to read the image, convert it to RGB format, and show it using matplotlib. And the next one is going to be the load image function. We are doing roughly the same thing, but this one accepts an optional parameter which is set to true, which basically resizes the image into a square. And I'm going to show you why this will be useful in a bit. Alright, so one good way to basically have a look at the images or a couple of images is to basically draw a grid from the images. So I'm going to define a function called showSignGrid. And this one is going to accept a list of image paths. In here I'm going to load all of the images. For image in image paths. Then I'm going to convert those images into a single tensor. Recall that this is actually a list of NumPy arrays. So each image loaded using OpenCV is just a NumPy array. So we're going to convert or concat or merge all of this into a single tensor. Next, I'm going to go ahead and basically permute the color channels of this tensor, so we can use the torch vision you use make grid to create a grid image of all those images. I'm basically saying in here that I want the blue color to be first in here, then I want the red color, and then I want the green color at the last place. Then I'm going to basically just build a grid image using torch vision, use make grid, and this accepts the tensor of with the images. And then I'm going to specify the number of columns, which is n row I know. Here I'm going to pass in that I want 11 image or 11 columns or 11 rows, however you want to call it. Next I'm going to do a setting that will tell that the image that I'm going to show is going to be slightly larger than default. I have 16 by 8, let's say. Then I'll show the image itself, but again I need to permute the channels, so Matplotlib is able to show this. Alright, so the next thing that I'm going to show you is how you can basically sample an image from each traffic sign class. For each train folder in train folders, I'm going to use NumPy random choice and use glop to list all of the files in here. I'm going to take each image, convert it into a list, and get a single image from this list. Okay, so I'm going to call showSignGrid sample images. And if we let this run, you can see, let me reduce the size of this into 14.7. Alright, so you can see a grid containing each traffic sign, a sample of each traffic sign. And you can see that we have a lot of speed limit signs at the first row. We have the classical priority road, stop, give way, no entry, and other traffic signs that you should be able to recognize every one of those actually. And this will basically end the exploration step for our dataset. Okay, so the next thing that we're going to do is to build a dataset that is based on this original dataset. And this might sound a bit strange, but the reason for building a subset or using a subset to build a dataset is that this dataset is actually very imbalanced. So I'm going to start with a simple problem, and then you can basically try to expand on this. The simple problem is going to be to build a dataset that contains only 4 different signs, and those 4 different signs are going to be the priority road, the giveaway sign, if you see this one, the stop sign, and the no entry sign. The no entry sign. So in here, I'm going to continue with building that data set. And I've already told you the class names and the class indices of those. The class names, and these are the indices in which every one of those, so these correspond to the indices in here, if you take a list from this one. And the indexes of this one correspond to the different class names here. So let me begin by creating a new folder that we're going to call just data. And in here, I'm going to basically create a split for the train data, for the validation data, and the test data. And we're going to use the train and the validation data to basically evaluate and train our model. And then we're going to have a look at how well does our model do on the test data. So I'm going to just go ahead and start by making the folders. Data, train, and I always say that exist is fine. Then for the validation, and then for the test data. And then for each class name, I'm going to create a subfolder in these ones because, this is a standard format that you can use when you're training an image classifier. So there are helper classes called image folder, which are basically able to create a data set from a folder of images if they follow the proper format. And we're going to have a look at how you can do that right now. So for each class in class names, I'm going to basically get all of this, paste it in, and then I'm going to just paste in the class name here. All right. So class names is not defined. Yeah, I have to run this one. Okay, so if we have a look at the directory structure or the directory tree, we have the train, test, and validation subfolders, and for each class we have a subfolder in here. So of course those subfolders are currently empty, and we will have to basically get the images. All right, file move out, that's good. Okay, this looks fine. Okay, so basically the next thing is going to be to do some copying of the images to the correct subfolder. So I'm going to go ahead and paste in the code for that because it's a bit verbose. And for each index in here from these ones, I'm going to take the class image, the class index, and I'm going to take all of the images in this class using glop again and convert this into a NumPy array. So I'm going to also take the class name. So this will be the name of the class, of course, and that is corresponding to this class index. I'm going to print out this, and then I'm going to shuffle the images because, well, they might be some strange order at which they were probably created, but I'm going to shuffle them just in case. Next, I'm going to use NumPy split. So this is an interesting function, and I'm going to go ahead and basically do this so you can see what is up in here. Okay, so this NumPy split allows us to create a train, validation, and test subset from this particular traffic sign using indices or sections. So in here, I'm basically saying that I want 80% of the images to be spent, to be put into the training subset or set. Then I want the 0.9 minus 0.8, which is 0.1, to be put into the validation set, and the remainder, which is 0.1, of course, to be put in the test set. So you might be, or you should be actually very familiar with the train test split used by the scikit-learn, or provided by the scikit-learn library. But this one, NumPy split, is also very good, and it allows you to split your data in n different partitions. If you, of course, if you use this format and understand what the indices or sections mean. So this is very, very good. I didn't know about this one. And next, we are just iterating over each image in the train, the validation, in the test set, and putting it into the correct folder and copying it to the correct class name. So let me execute this. And as a bonus, we are receiving the output, which tells us how many examples do we have in each, for each traffic sign. And you can tell that we also have quite a lot of imbalance in here, but this is this is kind of okay. Of course, the stop sign is not very well presented, so we are going to check the accuracy for this one later on. All right. So the next thing that I'm going to show you is how you can create transforms that allows you to basically augment your image training or validation and test datasets. So I'm going to use the transforms that are available from Torch Vision. I've also created a video which is using Augmentations library, which is basically provides you a very nice interface for creating amazing, really amazing transformations for images, augment images. But the Torch Vision transformations library or submodule is very good as well when you want to do something, let's say, a bit more basic. Not that there are really transformations that are very good. There are really transformations that are very good, but the Augmentations library is pretty fast and simply amazing. All right, so I'm going to copy and paste the transformation code. Because it's a lot. And we have transformations for each subsets, for the train, for the validation, and for the test set. And the transformations are just compositions. So in the training data, we are doing some cropping, we are doing rotation, we're doing horizontal flipping, and finally we are converting all of this because this one expects an image or pew image. This transformation basically converts the pew image or pew image array data to PyTorch tensor, and then we are doing normalization, which is expected by the pre-trained model that are provided by the Torch Vision. I'm going to put a link into the normalization or the requirements for the pre-trained models in here. And you can see that we are basically, we are just, we are converting those images into 20 or 256 pixels. And this is also required by the pre-trained models, at least for the ResNet models in Torch Vision. Okay, so let me execute this. And the next thing that I'm going to do is to build datasets. So let me go ahead and say that the data directory is going to be data. And then I'm going to create a dataset for each subset of data that we've already created from the training, for the validation, and the test set. And I'm going to use the datasets.image folder dataset, which basically helps you create this. I'm going to do some datasets, image folder, and this one expects a root directory and then transform. The root directory is going to be the joint path of the data dir, which we already defined, and the current subdirectory, and the transform is going to be the chosen transforms for this particular subset of data. Let me expand this like so. Okay, so now that we have the image folder data set, I'm going to go ahead and do the iteration over the train, validation, and test sets. Let me execute this. All right. And of course, when you're building a data set, you need also a data water. And the data water that I'm going to use is going to be based on the Torch Utils data water. So it will be just a basic one. And this one accepts the dataset. Then I'm going to pass in the batch size, and I want to have 4 images per batch. Next, I want to shuffle the data, and I want to specify the number of workers, which is going to be 4. So we have basically 4 workers that are loading the data for us. And then I want to iterate over the same subfolders as in here. All right. So the next thing that I'm going to do is to check if we have the CUDA available accelerator. I'm going to take the dataset sizes for each one, so how many examples do we have in each dataset, and I'm going to basically record the each class name. So let me start with the check of the device, and this will be CUDA if we have Torch CUDA is available. Else is going to be just a CPU. Next, I want to take the dataset sizes. Okay. And finally, I want to take the class names which are available from the datasets themselves. So I'm going to just take in the training dataset and take the class names. Chosen datasets. Really bad naming convention, I guess. Alright, so the next thing that I'm going to do is to define another function which is called imShow. And this one will show us an image that is taken from a data water that we've already defined. And here I'm going to use the train data water to take a batch of images. I'm going to convert this into a grid. And basically use the function from above imShow to show the output and use each class name and show this into the title. All right. and you can clearly see that the transformations are applied to some of the images. We have some rotation, some random cropping. So this probably should increase the accuracy of our model, because we are creating even more training data for the model, and it's been shown empirically in a lot of papers that at least I've read, that image augmentation really is helpful whenever you are training a convolutional neural net. And we're going to train a convolutional neural net, which is going to be based on a ResNet architecture. But our dataset is very well done. At least I hope so. It's a really beautiful one. We have to basically create a model and use that model to recognize traffic signs from images like those. So there is a simple, or let's say there is a way to do this and to start from scratch, create a convolutional neural network. For example, in our case, this might be quite good because we have images and we have image classification problem. And we might start by, let's say, creating a simple convolutional neural network, then trying to optimize the architecture, optimize the parameters, and go through all of this. And basically, we might not still get as good model that we are going to get using basically the technique that I'm going to show you right now. And the technique I'm going to show you is, of course, we're going to use a pre-trained model. And the pre-trained model is going to be based on the pre-trained model available into the Torch Vision module, which is called ResNet. The ResNet architecture is very interesting, and I'm going to link this blog post into the description, which blog post is Augustinus Christidiadi. I'm not sure how to pronounce this name, but this blog post is very good. Good job, mate. So the basic intuition behind the ResNet architecture is that, well, when you're building very, very, very deep convolutional neural nets, you expect that when you're adding more and more layers, the neural network is your expectation should be that the neural net is going to be more and more accurate, because you're basically putting more and more parameters in it. So some of the deep neural nets that you might have seen, this is, for example, ResNet 34, and is going to be the architecture that we are going to use. You can see that we have a very, very deep neural net in here. And in practice, when you do this using conventional convolutional layers, it turns out that in practice, again, you do not get better models. Actually, the performance degrades thanks to the curse of dimensionality problems and the vanishing gradient problems. So basically, the signal of the input is worst when you have multiple layers. So let's say it, this is just a hack. One hack to overcome this issue is to basically go with the input, pass it through the network, but also provide an identity function which basically feeds the input directly into the output of the layer. So you have at the output layer, you have this equation, which is basically the approximation from the weights of these layers in here, and then you have to add the input itself. So whenever the network decides that basically the function approximated in here is pure garbage, you can just skip all of this by saying that you're inputting 0 in here and just outputting the input. So you can basically do a dropout or eliminate the subnetwork altogether. At least that's or just basically skip this subnetwork. When the value of this function actually is 0. So you can read a lot more in here. And of course, you can read about this into the original ResNet paper, which I'm going to again link into the tutorial that is going to be available for this video. So how can we use the ResNet in PyTorch? Torch Vision provides a lot of pre-trained models, and I'm going to show you how you can use those. Alright, so here I'm going to define a function create model, which is going to basically create a ResNet model, do some adjustments that should be available for our case, and finally return this model so we can train it. Alright. And here the only parameter that I'm going to pass in is going to be the number of classes that we have. First I'm going to create the model, and this is available in Torch Vision Models, ResNet, and I'm going to take the 34 layers, and I'm going to pass in the pre-trained true. So I want a model that is already trained on some dataset, and this one is actually trained on the ImageNet dataset. Alright, so the next thing that I'm going to do is to basically replace the last layer, which is a fully connected layer, and I'm going to basically replace it with a linear layer that has the number of classes as an output, and then I'm going to put at the end of all of this a softmax function, because yeah, we are doing a multi-class classification problem, and our linear layer is going to expect a number of input features, so I'm going to first take those, and this is going to be based on the model from the fully connected layer FC. I'm going to take in features. Alright, and then I'm going to replace the fully connected layer with NN sequential. So this is the sequential API that PyTorch is providing, which you can use to create a model without actually extending from Torch NN module. And in here I'm going to put in a linear layer, get the number of features in here, and the number of classes as an output. And as I've already discussed, I'm going to assign a softmax function or layer at the bottom of it, and I would like to apply the softmax function across each row of the predictions. So each row in the output is going to be summed up to 1. And finally I want to return the model, but first I'm going to put it onto the device that we're going to use. In our case, this will basically move the model to the GPU. Alright, so using this function I can create a base model, and we are actually going to reuse this function, and you're going to see why in a little bit. Here I'm going to pass in the number of class names, and something magical is going to happen right now. You can see that the pre-trained model is just a PyTorch checkpoint, which is available from this URL, and PyTorch Torch Vision is smart enough to download it, and it's a bit hard to see, but this model is 83 megabytes. You can opt out for larger models. They will train a bit slower, but might be very accurate compared to this somewhat basic model. But we are going to start with simple models, and then if we only need something more complex, only then we are going to go ahead and basically do the complex ones. So this is a practice that I'm doing in my work. Alright, let's continue with training the model that we've already created. So I'm going to go ahead and put a section training our model. And the code that is used for training the model is quite long. I'm going to paste it in and run the cell in here. So we have the train model function, which accepts a model and the number of epochs that we're going to train our model for. And we're using the was function cross entropy was because we are doing multi-class classification. We are using a stochastic gradient descent optimizer, which accepts the parameter of our model. We have a warning rate set and a momentum, and we have a warning rate scheduler, which we are basically not going to need, but you might want to see how you should structure your training code in examples like this. We have the best model weights, which we will record based on the best best validation accuracy that we achieve. And then for each epoch, we are going to go into two phases for the training and the validation phase. We are going to check and put the model into a train or evaluation mode. So basically, the evaluation mode in PyTorch will turn off something like, I guess, dropout and a couple of other options that might be available. And during training, those dropout and something else is turned on. So for each data point or batch sample, we have to put the data onto the GPU. Then we're zeroing the optimizer because if you recall that PyTorch is going to otherwise accumulate, or the optimizers are going to accumulate the gradients, which is something that we don't want to do. And we are basically going to turn on or off the accumulation of gradients only when we are in training mode. And we're going to take the model output, get the prediction classes by just taking the maximum value in here. This will be the predicted classes. Then we're going to calculate the was based on the real classes and the outputs of our model. And if we are in training mode, we are going to propagate the error and then do an optimizer step. We're going to then calculate the was and the number of correct examples that we've seen. We're going to do the same thing for the epoch and for the was and the accuracy. And if we are into a validation mode, we are basically finding the best validation accuracy so far during the training. We are just going to copy the model state and use those weights as the best weights that we currently have. And if we are currently training for each epoch, so remember that you should call the warning scheduler only into the training phase and only once for each epoch. Here I'm calling the scheduler, the warning rate scheduler .step. Finally, I'm basically printing out the best validation accuracy and loading the best weights that we found during the training. So this is pretty standard stuff, but yeah, you might wanna have a better look at this method. The next couple of functions I'm going to just continue with. Let's first try this one. Let's just train the model. And I'm going to say that I want to train it for 3 epochs. So this should take some time. And during this time, I'm going to define these 2 functions. Get predictions. In here, I'm going to put the model into evaluation state, and I'm going to get 2 lists, one for the predictions and one for the real values. and I'm going to use the context with torch no grad, so I don't want the gradients to be calculated in here. And for each input and labels in each batch in the data order. Alright, so you can see that after the 0th or the first epoch, we have an accuracy of 99% on the validation set, which is extremely good. And the training accuracy is still quite low though. Well, we have, of course, a much smaller validation data set. And this can be expected because, yeah, we have, of course, imbalanced data set too. So let's see how the training and the validation errors are doing on the next ones. Okay, so next in here, I'm going to take I'm going to paste in this code, put the labels and inputs onto the GPU device. I'm going to take the outputs of the model and get the predicted classes. And I want to take each max value along the rows, not the columns. I'm going to add the predictions and the real values. Then I'm going to basically convert the predictions to a tensor, and I'm going to put all of this onto the CPU, and I'm going to do the same thing for the real values. And finally, I want to return the predictions and real values. And I'm going to run this. So the training was quite fast, and as you can see, we have a training accuracy of 95% after 3 epochs and 99.84 accuracy on the validation set. So you might want to try to maybe train a bit longer, but this should actually be pretty much fine for us. Alright, so the next function I'm going to show you is going to be the one that we're going to need for evaluation of our model. So basically get predictions is going to be in this same section. So the next thing I'm going to do is copy and paste the next function, show predictions, and let's walk through this one. This one accepts the model, the class names, and the number of images that we want to show. So we are again turning the model into putting the model into evaluation mode, and we don't want to again accumulate any gradients or calculate any gradients in here. And we are just iterating over the test set. So we want to see how our model is performing on the test set. So here we have the inputs and the labels put on the GPU. We have the outputs. Basically, this is the same thing that we've done over here. And then for each image, I'm going to just plot the image and the predicted class name for this image. So let's basically continue with using this function, show predictions, paste in the base model, the class names, and the number of images, which is going to be 8. We just want to see 8 images. Alright, so priority road, giveaway, priority road, stop, stop, giveaway, giveaway. So this is actually very, very good. Alright, so let's have a more comprehensive view over the model performance. And we're going to get the predictions from the test set. Get predictions, base model. And we are passing in the data orders test. Okay, our function is running, And next I'm going to print the classification report for the real test data and the predicted test data, and I'm going to pass in the class names that we have for the targets. Wow, as you can see, we have a very good model on our hands. It's basically perfect. So this is very good job. The next thing that I want to show you, which of course in here might not make any sense at all, because we've seen that we have perfect precision and recall for each class, is to how to show a confusion matrix. And I'm basically using the Seaborn heat map function. I'm rotating the labels and putting true label and predicted label in here. The next thing I'm going to do is to create a confusion matrix using confusion matrix that is provided by scikit-learn, passing the true and predicted values. Then I'm going to convert this into a data frame. I'm going to put the class names as index, and the column names are going to be the class names again. So finally, I'm going to show the confusion matrix using the data frame that I've just created. And you can clearly see that we have, we have one misclassification. So this is probably a rounding error in here. So we have one misclassification, and the misclassification was that the true label was priority route, but our model said it was giveaway, which is very interesting. But recall that both, so it messed up this one with this one. That's interesting. Okay, so let's continue with basically doing a prediction on an image that our model haven't seen. And it's image that is basically not from the same dataset at all. So let me just download it. This is hosted on my Google Drive, so you should be able to see this image. And I'm going to use the show image function that we've defined at the top, stop sign.jpg. Okay, so we have an image that is very different from the images that you've seen into the dataset. How well will our model be able to cope up with this? And to understand the prediction of this one, I want to create a function called predictProba or predict probability that will basically predict the probability for each available class given an image. And if this is nowhere near clear, I'm going to just do it, and after I show you the diagram or the plot, you should be able to get what I'm saying. I'm sorry. Take the model and the image path, and first I'm going to load the image using PewImage. Then I'm going to convert the image to RGB format, and I'm going to apply the transformations from the test set, because this is a test image, and I'm going to remove one of the dimensions. So I'm going to flatten it. I'm going to take the predictions from our model, and I'm going to pass in the image that is passed on to the GPU. And I'm going to take the prediction, convert it into a NumPy, and flatten it. Alright, so let's predict the proba for this image that we have. Stop sign JPG or JPEG, and let's see the output of the pred. And you can see that these are basically the different probabilities for each available class. We have 4 classes. Recall, let me show you the class names. So giveaway, no entry, priority route, and stop. So given this information, let's create a data frame of the predictions. Put in the class names. And the values. This autocomplete is killing me. Of the predictions. Then I'm going to use Seaborn bar plot to basically show you the predictions from our model. The x's are going to be the values, the y's are going to be the class names, the data is going to be the prediction data frame, and I want to orient this horizontally. And this is the result, which is amazing actually. Our model is very, very certain that this is an image of a stop sign. And recall that this is a random image from the internet, which is nowhere near as similar to the other images in our dataset, which is pretty amazing, I guess. Okay, so let's continue with a sign that is from our dataset, but it's not actually included into the images or the indexes that we are basically showing around. So let's get the no truck entry trying out with no truck entry sign. And this one should be very interesting. So the index of this class is 16, and I'm going to take a single image from this. .ppm, I guess, yep, and take, let's say, the first or the second element from here. Next, I'm going to basically do the same thing that I've done here, but I'm going to pass in the no truck path. And again, I'm going to create a data frame with the predictions, class names, and values. I'm going to show you the image that we're looking at. So this is the sign. And well, you can stop in here and think about it. What should our model say when it sees image like this? So one good response, I guess, for this would be to just say that it's really not certain in any of the classes. So it would be a good, hopefully a good idea to have an equal amount of probability or certainty in each class. So I would expect a uniform distribution. But let's see what our model really thinks about that. I'm going to just copy and paste the same bar plot. And the result is, well, so our model thinks that is almost 60% with almost 60% certainty that this is a stop sign. So, and it's a giveaway sign. So, well, when you're building a self-driving car and when you see this sign, and if the car is actually a truck, if your model understands this as a stop sign and then the truck stops and then continues on its way, of course you're going to break the wall. because your truck that is trespassing into an area that is not approved for trucks, I guess. Okay, so how do we solve this problem? So one way to solve this problem is to add a new class, which is kind of a meta class or a dummy class, which we are going to call class unknown. And this class is going to be a mixed bag of all the other examples or all the other traffic signs that we have in our dataset. So I'm going to show you how you can build this. And hopefully this should solve the problem of having signs that you don't really know about, because, well, in the real world you might actually not have enough or examples at all for each available class, and you might just be interested in knowing that the class that you're seeing is something that you don't know. And then you might say, if you're, for example, building a self-driving car, you might say to the driver, well, you should decide in here what to do next. So let's continue with adding this class unknown. So this is like an alien vibe in here. Okay, so we are going to basically take all of the classes that we haven't looked at, and we are only going, let me reformat this for you. We are iterating over each training folders that we have, and we are skipping the class indices that we have, and we are also skipping the no truck index. So we are going to really emulate or simulate the case that our model has not really seen any examples of no truck signs. And after that, we are going to just create these unknown indices, and then I'm going to basically create the folders that we need for this class. Let me show you the code for this. For the training, validation, and test set, we are building the unknown class. So we are adding these folders, and in each, for each index of those classes that we've picked, I'm going to take 50 examples at the most. Sometimes those might not be 50. And then I'm going to basically do the split that we did for the other examples or other classes that we had. So I'm just adding a new class with a lot of data in it. And this should probably run just fine, actually. Okay, so I'm going to continue with defining the datasets and data orders and dataset sizes and class names just in the same way that we did already. So I'm going to just copy and paste the code for that. The datasets, then the data orders, the dataset sizes and class names, and the class names right now should be giveaway, no entry, priority, road stop, and unknown, the new class that we have here. And let me check the dataset sizes. No. Let me just go ahead and grab this. We have 764 examples in the training data with the unknown class. So this class is somewhat well represented using the 50 at most examples for each sign. And next I'm going to build or create a new model, and I'm going to call it the enhanced model. So this is no longer a nutty model, if you know what I'm talking about. We're passing in the class names. And next I'm going to train this model using pretty much the same procedure as before. And again, I'm going to train it for 3 epochs. This might take some time. So I'm going to just pretty much get the data. Going to just copy and paste these cells from here. I'm going to copy the cells, copy selection, hopefully, and go down here, paste them, and I'm going to replace the base model in here with enhanced model, and hopefully this should give me a much better result. Okay, so while this is training, I'm going to paste in the evaluation steps that I've already shown you how you can do. But this time I'm going to take those for the enhanced model. Let me just copy and paste these. All right. So this one is having a validation accuracy of 100% at the epoch number 2 already, and you can clearly see that we are starting at a bit lower training accuracy, and then the training accuracy is actually blowing up, and after this epoch is complete, we have 94% of training accuracy, and again 100% of test accuracy. So let me just predict all of this. So you can clearly see that we have 5 classes in here, and let's now run this. This is again the same image, and now we have a prediction of pretty much 100% accuracy, probability or certainty that this image belongs to class unknown. And recall that our model haven't seen the no truck entry signs whatsoever. So this is pretty amazing. Next I'm going to show you some predictions from this model. We have the unknown, giveaway, stop, unknown. This looks very good, in fact. I'm going to get the predictions from this model and print the classification report. You can see that our model is again doing very, very well. And the confusion matrix this time around looks pretty perfect to me. So now let me just check. Yeah, we have 38 plus 1, 39, and when we add the 4 we have 43. So yeah, I think that we don't have the unknown indices. Let me just make sure that no truck index is 16, and you can clearly see that the index 16 is missing from here. So I just wanted to basically double check that we are not including the train, the data for the no truck path. sign. Okay, so this is pretty much a great way to build a traffic sign recognition model. And I'm going to put a tutorial and link to the notebook into the description. Thanks for watching, guys. Please like this video, subscribe, and I'm going to continue with these PyTorch tutorials. I would like to thank you very much for the huge subscription, the huge amount of subscribers that I've gathered with the last video on the coronavirus. And I know that it's a bit, the WHO now declared it officially a pandemic, so the things are pretty tight, I guess. But thank you for watching. I'll see you in the next one. Bye bye.